Thank you, Cyprian, for the introduction. So, first I would like to thank the organizers. So the winter school has been always my favorite since my PhD time. More than 10 years ago. So, and also thank you all guys for coming and stay the very last day, and coming in the cold morning. I'm Zhenguang Liu, and I'm going to talk about fractional quantum anomaly Hall, or FCI, and unconventional superconductivity in rhombohedral graphene. So this will be an experimental talk. So hopefully, with all the experimental evidence I give, you can gain more confidence about, how rigorous this state is, and there are so many unsolved problems. So the cover is actually one experimental curve of RxX. So I just decorated, and you can see it's a quite nice RxX curve. Just look like a quantum Hall states you can get in high magnitude field. So first I would like to start by acknowledging all the people involved in the work. So most of the stuff I'm going to talk about is the work done during my postdoc in Long's group at MIT. And there are some of the new data we acquired very recently by my group at Florida State. And we also collaborate very closely with our local experimentalist Ping and the theorist Cyprian. And also we got a lot of help from the theorist Liang and Ban Zheng. Also experimental-wise by Dominic for the low temperature, and reassuring for the compressibility measurements. And of course, we got the high-quality HBN from NIMS. So I don't think I need to mention much more about this. So if we partially fill along the level, so we can get this beautiful effects of fractional quantum Hall effects, where you have the XY that quantized to a fractional number times h over e squared, and associated with a dip in RxX that's supposed to be dipping to 0. So and there are so many implications about the fractional quantum Hall effects, and it really gives like a new concepts of fractional statistics, and we have been learning a lot from Professor Jen Janara about the composite fermion theory, and also it has a lot to do with the proposed quantum computation. So with all these beautiful experiments and the future application, so experimental-wise, you can see it's few tenths of Tesla and a very low temperature, right? So if you don't mind coming to Tallahassee very often, then probably won't be a big deal. But still, it's a very extreme condition. So there has been like question, both fundamentally and practically. So if it's possible to see such effect at zero magnetic field, right? So there has been a group of paper that is publishing around 2011 pointing out, in principle, it's possible. And if I understand it naively, so you should find something that mimics the Landau level. So in short, you should have something that intrinsically has a topologically non-trivial bands, and the bands should be flat and isolated with other bands by a well-defined band gap. All right. So if we look at for example, in material-wise or device-wise, how it develops, like since the discovery of the fractional quantum Hall, right? So of course we have the well-known gallium arsenide quantum well, and later on it's also been discovered in, for example, zinc oxide quantum well, or silicon MOSFET, and now also in the van Waals materials like graphene and other van Waals materials as well. But for example, the topological materials that we are aiming for isolated topological bands, but now we know the answer, right? So we have two systems that shows the fractional quantum anomaly Hall. One is twisted MOT2, and one is a rhombohedral multilayer graphene aligned with HBN. But if we do not know the answer, So it's a huge disaster, right? So it's across the whole periodic table, and it's almost impossible to find anything, just like you're looking for a needle in a haystack. So, well, I mean, the good thing is like we have a lot of good theoretical guidance. For example, in the TMD system. So the twist TMD is, first proposed by Allen's group, and then the specific material system, the twist MOT2, and then later on, it's calculated by Shizeng and Liang. So it's being pointed out specifically, you can have such flat trim bands with a certain twist angle. And with few years of experimental efforts, so this has been found or discovered at 2023 in both electrical transport and also thermodynamic and optical signatures. And you can see the data gives you the plateaus at the fractional filling for the RXY, and you have dips in RXX. So so this is one line of the exploration of the material system, which is the TMD system. So of course, there's another very good system, which is a graphene system. So this has been first thought and explored in the sense of the famous twist bilayer graphene, as well as the string graphene. So indeed, like if you look at the theory, so you also should have isolated trim bands in this case. And there are lots of efforts also experimentally try to measure it. So first, you can see actually the ferromagnetism has been observed in TPG, like in David Goldhaber-Golden's group. And following that, actually the integer quantum non-Paul effect has been discovered by Andrew Yang. And so far, the best try is actually from Amir Yacobi's group. They use a scanning single electron transistor that can locally measure the compressibility, and they saw signature of the fractional Chern insulator around 6 Tesla. So, but so far that's the best try. So you're not really nailing down such state as zero magnetic field, and it's not really a transport measurements. So the problem here, the issue here, is actually coming from the so-called twist angle inhomogeneity. So you have two layers of 2D materials, single layer 2D material. When you twist it, it will naturally relax to a certain angle they lack, right? So not necessarily the whole device will give you a unique, just a unifying angle. So as you can see here, if you map out the angle, it's like a pretty large variation, and this actually will kill whatever the property you can measure globally, for example, like transport. So so far this is sort of like the best efforts along the twist bilayer graphene. So we'd rather to go the other road, which is actually just natural graphite. So the sample we are using is just like a kind of natural graphite piece you dig from the mining, and you just mechanically exfoliate, and you get such flake. And of course, it's not like a random graphite. So it's with certain stacking orders. So you have two kind of most common stacking order for graphite. One is called Bernal stacking. So basically you stack the sheet back and forth. And the other is called rhombohedral stacking. So you keep stacking it along one direction, which is forms sort of like a staircase form. So, but do aware, like if I say something like stacking, I didn't mean like you have each different single layer and you like manually stack them together. So rather than like you just exfoliate from the bulk graphite, so this will just naturally exist. So, and then you can use some optical method to separate these two stacking order because of the optical conductivity difference. So you can see like in this case, you have a pretty big difference between the ABA stacking and so-called ABC stacking. So yeah, with this kind of staircase form of the graphite is what we're interested in. And it's actually metastable, but it still naturally exists, which is about like 20% in natural graphite. So yeah, with this kind of staircase form of graphite, so let's see if we can get really like a isolated topological flat bands, and which may lead to the fractional quantum anomaly effects. So starting from the band structure of the rhombohedral graphene, so I think Andre already gave a very clear explanation. So it basically just SSH model. So the low energy band structure is dominated by the two corner A1 and Bn site, and the dispersion follows the k to the nth power. So which means if you have thicker and thicker graphite, you get flatter and flatter band structure at the low energy. So this actually gives you more or less like a pristine flat bands, although it doesn't really look like a perfect flat, but well, much better than single layer and bilayer. So because it's a 2D material, then we can utilize the advantage of the van der Waals material to form such like a parallel plate capacitor structure. So you sandwich whatever the material you're interested in by two dielectric layer, and then you add two metal layer on top and bottom to form the this parallel capacitor. So then you can thinking about individually changing how much you dope the electron or hole, or how much you change the electric field. So if you put different charge on two sides, then you're adding an electric field, right? So if you're putting the same charge, then you're changing the doping. So by adding the electric field in the rhombohedral graphene, so you're breaking the immersion symmetry and opens up the band gap. So at the same time, you can also tune the bandwidth of how flat it is. So you actually have a naturally exist relatively flat bands, and then you have a continuous norm that you can tune the flatness of the bands. So I mean, all sounds pretty good. So basically, we already have the first one checked, right? So you do have a flat bands, and it's not only just from kind of like the calculation. So you can also have, I mean, all this experimental evidence. For example, so this is a tri-layer graphene. So the horizontal axis is how much you dope, and the dope electron or dope hole, and the vertical axis is the electric field you add across the sample. So at the zero doping and zero displacement field, you should have the band crossing there, and you should expect something like metallic behavior, right? So which should also be true for thicker layer, right? So you also have a lot of density of states here, which should be a kind of a good metal. But rather than metal, you can see this is a pentalayer, which is 5-layer. So at 0N and 0 electric field, it's actually a very good insulator. So that means like at here, you already have like a gap opening by the interaction that's driven by the flat bands. So yeah, you have some flat band effect. And how about the topology? So I mean, yeah, go ahead.
Where did this gap?
Oh yeah, this is from the context.
Exactly.
Yeah, that's artifact from context.
Yeah.
So okay, so yeah, you have the flat bands, and actually graphene is also a topological material, right? So in monolayer graphene, you have a pi barrier phase, and if you have n layer of graphene, you have an n pi barrier phase. And if you apply electric field, open up the band gap, you expect the barrier curvature will concentrate around band opening, like area, and by tuning the electric field and the doping, you can actually selectively tune your the barrier curvature you see. So yeah, I mean, then you're probably going to expect something like it's non-trivial in terms of the topology. So yeah, we're kind of like crossing the second one as well, and there's also a lot of experimental evidence. It is indeed topologically non-trivial. So for example, this is a pentalayer graphene device, and it shows C equals to 5 Chern insulator at about 1 Tesla. And it can also be stabilized by approximatizing spin-orbit coupling, and it can bring this Chern insulator down to 0 magnetic field, which is the integer quantum anomaly Hall effects. So okay, so it sounds like you have a flat band and it has non-trivial topology. So is it really isolated, right? So if you look at the band structure, So it's flat here, but it has a pretty sharp curve on the two sides. And Andre gives the name as a very trash can, right? So you have this very sharp turn on the both sides. It's not really isolated. And this is a big issue. So you need to probably find some way, like serve as a scissor that can cut off the bottom of the trash can. So the scissor is a moire. So if you form moire potential with, for example, HBM, then you truncate your Brillouin zone, right? So you can select your moire potential, or your moire wavelength, and then you basically select the size of your Brillouin zone and how much you cut off. So for example, this is a band structure of tri-layer graphene, and if I add moire potential with HBM, so you basically have the band folding. And then if you add if you add electric field of outer plane, so you're sort of further squeezing the bandwidth. And it's not perfect, but it looks somewhat flat, right? So with all this tools, so you sort of have like isolated topological flat bands in the system. So although it's all pretty hand waving, but let's see if in this way we can actually have fractional quantum annulti effects. So the experimental setting is you have a 5-layer rhombohedral graphite in the middle. So because the band is relatively flat compared to the thinner layer, and then you have one side that is aligned with HBM that's forming the moire superlattice with a wavelength of 11.5 nanometer. So so it's forming on the top, sorry. And then you can apply electric field to open up the band gap. So, and also when you're applying electric field, you're actually pushing your electron towards one side of the device, right? Because it has finite thickness. So in this case, we have the moire potential on top, and we have all the electrons that push to the bottom. So this I'm going to probably repeat like multiple times. So the moire potential is on the far away side of the electron. So with this setting, so we make the Hall-Bar device, and you measure transport of RxX and RxY. So on the left side is the longitudinal resistance, and on the right side is the Hall resistance. So and again, so the horizontal axis is the charge doping, the hallmark charge you dope into it, and the vertical axis is the electric field. And you can also convert it into this filling factor. So filling factor 1 means I have 1 electron per moire side. So from this color plot, you can already see a lot of abnormal thing. So first, there's a pretty important thing is you can see the number of the electric field is almost like 1 volt per nanometer, so which is really high, and it's close to the breakdown of the dielectric. So basically, that means I really push hard, the electron that is far away from the moire potential. So from the longitudinal resistance map, we can see there is a very clear dip that is aligning with filling factor equals 1, and there are some features that may be aligning with certain fractional filling. And around this region, there's actually a lot of anomalous Hall signal. So both of the map are taking a 0 magnetic field. So basically, this blue color means a non-zero signal, and you can see actually the blue gives you already around h/e squared level of anomalous Hall signal. So if we look at more closely by doing line cuts, so on the left side is a line cuts around the filling factor equals 1. You get like almost perfectly 0 longitudinal resistance, and a very good quantization of the h/e squared. So that basically gives you an integer, a c equals 1 integer quantum nonce Hall. And if you look at the smaller filling factor, so you have this multiple staircase structure in the Hall resistance that is aligning with certain fractional filling factor that it also matches with the dips in terms of the longitudinal resistance. So this really reminds you about the fractional quantum Hall effect, right? So, but of course, it's not really perfect. So you can see the RxX is not really going to 0 compared to the fractional quantum Hall. And you do have plateaus, but I mean, they look rounded and not very sharp, right? So, and also we can check the hysteresis loop by checking, check the anomalous Hall signal by checking the hysteresis loop at different fractional filling factors. And it actually matches relatively well with the expected value of the fractional quantum anomalous Hall RxY. So, but one should be careful here. So, because I'm showing the hysteresis loop, but this is actually not a very good indication of quantization. So, what do I mean by that? So, for example, I take a measurement around 1/2. So, on the left side, so you have the RxY, which is like a tilted line, and you have the RxX, is kind of relatively like a flat line. And if I'm sitting at filling factor 1/2 and do magnetic hysteresis, also sort of aligning pretty well with the 2h over e squared. But I mean, you cannot call it's a fractional quantum anomalous states, right? So it's not really quantized. It's not really with a plateau in RxY, and there's no dip in RxX. So similar thing, you can argue that you can pick any kind of points along this flat line, or I mean this tilted line, and do a magnetic hysteresis. I mean, you can claim anything. So basically, one needs to be careful in terms of claiming all these states. So you should have a really good plateau for RxY, and you should have a really well-defined dip for RxX. And in addition to that, this should also match the strata formula. So and you need to make sure this state is gapped. So basically, when you measure the dispersion of the density versus magnetic field, so the slope should match with the Hall conductivity. So this matches pretty well for all the fractions. And so you can also cross-check with other experimental methods, for example, the compressibility, right? So you need to make sure this stays indeed incompressible. So so this is actually the work done by Reassuring. So he checked, actually this is an additional sample. So those kind of white lines, so those are 1/3, 2/3, and there's like more faint line, 2/5, 3/5. So when they are measuring the penetration capacitance, which is proportional to the inverse of the compressibility, then they can make sure at least, all these fractional states and also the interstates are all gapped. And they can also extract what is the gap value of those states. Yes?
Your RxX and RxY is what them to show that go the humans that and there's a lot and that
It's about 200 millikelvin.
and you have to them
Yeah, sure. So okay. So for that one, it's more or less like a I won't say experimental artifacts, but so you have your electron temperature that is separate with your lattice temperature. So even you do temperature dependence, it doesn't really mean anything. Your electron temperature saturates. So okay, yeah. I mean, with all this evidence, then you can like gain more confidence about saying, okay, this is the fractional quantum anomalous Hall states, right? So and actually, if we compare with the fractional quantum Hall states, I have a question.
things that then you do this like it that blatant can't
Oh, yeah.
that money that
Yeah, so basically, this is a little bit like a yield-defined density, because when you are adding more and more electric field, then your gap becomes wider and wider. So your zero density is actually starting with a tilted line instead of just from the center. So okay, yeah, if we compare with like the first graph from the quantum Hall, fractional quantum Hall effects. So there's also a pretty good quantization for RxY and a not so small RxX. Right, so if we compare the two, so they're more or less similar in terms of how good is the quantization and the rough RxX value or RxX residue. And also these two measurements are done by a relatively similar temperature on the same order of the hundreds of millikelvin. So the good thing is the fractional quantum Hall community has been so successful, and we can just learn from them, right? So how to improve everything. So I guess with few years, this is the fractional quantum Hall data in high field, and you see like a forest of fractional states with the improve of the sample quality and also lower your electron temperature. So this is done at 85 millikelvin. So we just follow the same route, just making better device and work on your fridge to improve the electron temperature, and this is what we got.
Yeah.
So you can see there are a lot more fractions, and with a very good quantization within about 0.1%. And you see like all these pretty well-defined dips, and before the residue is about kilo ohm, like few kilo ohm. Now you have few hundreds of ohm, and if you cool it down even more, it will just go lower and lower. So almost to zero. And if we zoom it in for example, RxX, so it really looks like pretty symmetric and follows all the gene sequence. So you also see not only 2/3, and you also see 1/3 here, because it's so close to, we suspect it's a Wigner crystal states, so you need probably slightly higher temperature to see the 1/3. But you do see them, which is about, I think 12 states or 11 states, and it's all in the gene sequence. Right, so if we compare the data we have now, I'll say like it's a year 2 of the fractional quantum nonce Hall with the fractional quantum Hall data at 85 millikelvin. They're not so different, right? So I'll say they're on the same order of data quality. So yeah, then it's just a matter of like you probably need to work harder on getting an even better device, and you improve your temperature even more, so to expect something new coming out. So yeah, I've been showing you the data from 2 devices, and so I guess it's better to talk about the reproducibility and how stable is the measurements. So I mean the first data is coming from device 1, and the better data is coming from the device 2, and now it's actually a pretty generic effect. It's not only in 5-layer rhombohedral graphene, also being seen in 4-layer, 6-layer in different groups. And at least now we have tens of samples that showing very consistent result. So yeah, this is like how reproducible is all the device. It's actually all because of the improvement of our sample fabrication process. Before, you only have like 1-2 devices that you can play around, because that takes years to make. And now, by using a certain optical method, that you can better see the difference between the different stacking orders. And so this will hugely improve the fabrication process. So before, you only get something like 2 to 3% of the yield, and now you almost get half, like 50%. So, and in terms of the time, I think the first few devices, it takes like a student about a year or more than a year for the fabrication. And now I think each student has few tens of devices in their hands. So that's how you kind of check the reproducibility and gain confidence about all this stuff. So and of course that's not all of that. That's just the second step, and then you need to improve the whole process of the more advanced version of the nanofabrication. So then now you have like sort of like a streamline of how to make the rhombohedral devices, and now it's just everywhere. So yeah, with the lower temperature and higher quality sample, so and you can actually see some additional stuff just other than the fractional quantum nonce Hall. So you can see this like different patches with 0 RxX. And actually quantize RxY, that quantize to H/E². And then it's extended to very broad filling factor. It's not really tied to a certain commensurate filling factor. So we call it the extended quantum nonce Hall. So and it only happens at very low temperature. So basically below a few tenths of millikelvin. So, I mean, the best way to understand is just dig into some old literature for fractional quantum Hall community. So people already see it for quite a long time, which is called reentrant integer quantum Hall. So you can understand it as you have a integer quantum Hall liquid, and then you start doping it, and the extra charge you dope into it that forms the Wigner crystal. So yeah, it could be one possibility. And there's alternative possibility that is called Hall crystal or anonymous Hall crystal. So basically, instead of you have an integer quantum Hall liquid plus a Wigner crystal, in this sense, like all the charge you put in, they crystallize. But the crystallize in a way is topologically untrivial. So you have an edge state of that crystal as well. So experimentally, it's hard for us to tell. So basically, I mean, we couldn't tell which is the case. So yeah, I mean, actually for the anonymous Hall crystal case, so if you believe that that is the case, it should spontaneously break the temporal symmetry as well as the translational symmetry, right? So yeah, I mean, this will be kind of very helpful if you can figure out the role of the Murray potential. Because if you already have the Murray potential, the Murray lattice will actually already explicitly break the translational symmetry, right? So there is actually a lot of puzzles in terms of like what is the role of the Murray potential here. As I mentioned, we push the electron away from the Murray potential, right? So I mean, what's the role of the Murray potential? And in addition, so I've been mentioning using Murray to cut off and to form isolated churn bands, but in some sense I'm lying, because even you add Murray and you do the band structure calculation, in the single particle level, you don't really have a separate churn band. So it's still all jammed together. So it's going to be, I mean, it's at least you couldn't understand in the single particle level, it has to be like an interaction-driven gap to separate the churn band. So yeah, I mean, there's a lot of things, like a lot of thoughts going on, and I'm just listing some of the theoretical work along this line, and so far there's still not really like a unifying theory that this can explain everything, but I thought, I mean, Andre is getting close, so yeah, hopefully he'll bring something new that can explain all these mysteries. So I mean, the only thing we know is, okay, Murray is important in this case to get fractional quantum anonymous Hall, right? So I mean, what if you get rid of the Murray? So you're starting from an even simpler case. So for example, for the anonymous Hall crystal case, if you get rid of the Murray, then your temporal symmetry and the translational symmetry still should be spontaneously broken, right? So yeah, this will be something like really informative to know. If we get rid of the Murray, instead of the fractional quantum anomalous Hall effects or the Hall crystal, we're getting superconductor. And this superconductor is like a very different superconductor from all the superconductor we already know, so which I'll explain later. So just by superconductor itself, it's not really like a news in graphene, right? So you have the tri-layer superconductivity, or I mean twisted bilayer. You have tri-layer superconductivity from Andre Yang, and so yeah, I'm adding line cuts to Andre Yang's cover plots, so it indeed goes to 0 very well. And actually, if you zoom it in, so it's actually fluctuating around 0 by few ohms. So, and the similar superconductivity on the whole side, so which is this bright color, so also being observed in a given seeker rhombohedral graphene. So in this case, it's this dark color. So it's at the similar phase boundary. And if you do line cuts of those, it's also going to 0 around few ohms. And it's rather like a kind of like a conventional superconductivity, and you can check the magnetic field dependence. So it will survive only up to about few millitesla in out-of-plane magnetic field. So, I mean, you can check like even seeker rhombohedral graphene, and something similar will happen. And also there's something new. It's like happening around the phase boundary. So the similar stuff also being seen by Matt and Andre by different layers of Romero graphite. So I mean, like what are the difference like for the superconductivity I'm talking about and all those observed superconductivity? So this one is at 4 and 5 or 6 layers, and so it happens at a similar space, like ND space, compared to the fractional quantum anomaly. So you need a really high electric field that pushes the electron to the one side. And at the doping of around like 0.5 or 10 to the 12th, so you see these batches of the superconductivity, which is a dark color. And the device itself is just a pure graphite. So there's no moire, just pure graphite. So then you can do some basic characterization of the temperature dependence. So the TC around like few hundreds of millikelvin. And you can do DIDV. And you can also zoom it in and check how good is your resistance to zero. And so this is around, I would say, 2-3 ohms near zero. So it's indeed the superconductivity. So without any residues.
But
yes.
So you said like with TTO, so that's like a noise flow up to start.
Yeah. So that's limited by your instruments. So okay. So yeah, then you can put this superconductivity in magnetic field. So it actually can survive to very high in-plane magnetic field. So these are the two superconductivity phase we have, and up to a couple of Tesla is still there and pretty robust. And this is not really where it disappeared. This just limited by our instruments. So up to here, you already see it's like a pretty large polylimit violation ratio, so which suggests it's a spin triplet. So more surprisingly, other than the in-plane magnetic field, it actually survives very high out-of-plane magnetic field. So this is very puzzling. So for the 4-layer Romero graphene, it can survive up to about like 0.6 Tesla out-of-plane field. So remember, similar TC superconductivity, like in tri-layer or 5-layer on the whole side, it can only survive up to 10 millitesla. So this survives to almost 1 Tesla. And for 5-layer, it survives to even higher than 1 Tesla. So this is something very bizarre. And even more striking, so other than surviving up to a very high out-of-plane magnetic field, it shows hysteresis behavior in the superconductivity domain. So what do I mean by hysteresis in zero resistance state? Right? So basically you start with a zero resistance, and then you start sweeping the magnetic field. And at some point, it has a jump, very sharp jump to finite resistance, and then jump back to zero. And then you sweep it back, so it's starting at zero and jumping back, jump to some certain value, and then jump back to zero. So this really looks like a magnet, right? So it's a superconductor, and at the same time also looks like a magnet. And you can also park at this inside this superconductivity states and at zero magnetic field and just watch it over time. Mm-hmm. It actually gives you the fluctuation versus time. So it jumped to some certain finite value and jump back to zero, and it's just jumping around. So yeah. Be perpendicular. So yeah, this one I'll show it in the next few slides. So yeah.
Be perpendicular. There, can you give what word?
Not really. I mean, this is something hard to say. Yeah, I guess it will be very helpful if, for example, one can do scanning squid. So it's probably possible to see. Yeah.
And but what's causing the jump? Because they quickly an avalanche.
Yeah. Well, I mean, it could be. So, so our naive picture is, so this is just something like a mesoscopic magnet that is not so far away from TC. You have the thermal fluctuation between the two values. So, okay, yeah. So actually the naive picture is like, so you have the superconductivity pairing within a single valley. So it's either from K valley or to the K prime valley. So you have multiple domains in the zero field in the sample. And if you have the domain wall that is across the sample, then when you are measuring the resistance, that will give you a finite resistance because the flipping the value will cause energy.
So it seems to me there's a more way. That's what I even point this in. We have to kill the zone conventional superconductor. You don't get a simple penetration of field, like widening ball. See nothing, and then all of a sudden, for the magnetic field, boom, you get what penetrate, when it freeze. Continue the rest of the field, it makes it get another.
Yep.
And that, I think, would have the same phenomenology.
Same phenomenology, but it will not have the magnetic hysteresis.
Yeah. If you're doing, it doesn't matter whether he's going to positive, negative, they're starting in zero. I mean, let me take that. Yeah, I think
okay.
you right.
Yeah. Well, yeah. So, actually, like answering the question just now. So, I mean, you have the hysteresis. I mean, how do I know? I mean, for example, if it's coupled to the spin or from the valley, right? So, because the superconductor itself is a 2D superconductor. So then you can sort of separate these two contributions by the 2D nature of the orbital. So for example, I can do this type of test. Like, for the orbital, it can only be either up or down. And for the spin, in the sense, because of the very weak spin of the coupling, basically can be pointed into any direction. Right? So, for example, if I use the in-plane magnetic field now, so to polarize the spin first. So, and then I sweep out-of-plane magnetic field. So if I still see hysteresis, that means it's from orbital, right? So because my spin is already being polarized. So, which is the case actually. So if I add the in-plane magnetic field and then I sweep out-of-plane magnetic field, so you still see hysteresis. And then you can do the other way around, right? So you can first add the out-plane magnetic field, and then your spin is fixed. Your orbital is fixed. So if it's come from the spin, if you sweep in-plane magnetic field, you should see hysteresis. But if you sweep in-plane magnetic field, in this case, you do not really see hysteresis. So yeah, basically this is evidence of, this hysteresis is coming from the orbital instead of coming from the spin. So this is something like a hand waving picture we have. So if you're thinking about this superconductivity pairing is within one valley, so then you can have like different kind of domain walls at zero magnetic field because it do not know to prefer K or K prime, right? So if you have a domain wall that is propagated throughout the sample, when you are sweeping the magnetic field, then this will cause the jump of the resistivity, and you push it back, then it has a jump on the other side. So of course, this is just like a guessing. So you need to give more evidence why I say the pairing should come from the single valley. So one evidence is like if you warm it up and you lose the superconductivity, but you check the normal states here, so you do see the anomalous Hall effect at this normal states. So you have the orbital magnetization. And you can also check the surrounding states. So this is the superconductivity states, and all the surrounding states that has a pretty large anomalous Hall effect. So basically, your superconductivity domain is embedded in like a phase with a pretty large anomalous Hall effects. And if you check the quantum oscillation, and you can sort of know what is the degeneracy. So it will give you the degeneracy of quarter metal, which means it's spin and valley polarized pocket. So and if we have a little summary about what we see, so the superconductivity is pretty robust against the in-plane and out-of-plane magnetic field. And we do see like magnetic hysteresis and fluctuations at B field equals to 0, and you have anomalous Hall effects at the state that is higher temperature when you lose the superconductivity, and also at the surrounding states. So basically, they suggest you may have a superconductivity that is from quarter metal. So, I mean, yeah, this is already suggesting a lot of things, right? So basically, it will suggest a spin triplet. And also because the pairing is coming from a single valley, it's definitely FFLO. And because of it's coming from like either K or K prime valley, so it's actually naturally chiral. So although we cannot tell if it's a P or P plus IP, but you already have the broken of time reversal symmetry and the mirror symmetry actually in the orbital level. So, and of course, this triggers a lot of discussions in theory, and I think Liang will tell about more details later. But this is indeed very intriguing. And again, I want to emphasize in terms of the phase space, if you look at what you get for the 5-layer rhombohedral graphene with and without moire, if you plot it in terms of the exactly same density in the electric field, so you will see by adding this very weak moire that is remotely or like 5 layers away from the electron, you can turn a superconductivity state into a fractional quantum Hall state just by adding this very weak moire potential. So, and the whole effect is actually very generic. So it's not limited by 5-layer rhombohedral graphene. So you can see it in 4-layer, you can see it in 6-layer. And there are actually more interesting stuff just, I mean, compared to what we have already seen. So for example, in 6-layer rhombohedral graphene, so which is very fresh data we just got here. So you have something like very similar phase diagram. So this is 2 patches of superconductivity, which is also have resistance and can survive to pretty high magnetic field. So more strikingly, if you do a line cut and apply autoplane magnetic field, so yeah, remember it can survive to pretty high, but in addition to survive to pretty high, it actually have more superconducting states coming. So these 2 dark patches, that's the superconductivity states that is we previously seen, and you have 2 very sharp phase boundary that is at plus and minus B field, and you have a new superconductivity phase coming out after this phase boundary. And it's at like around 1 Tesla, so you're using 1 Tesla of autoplane magnetic field induced a new superconducting phase. So, and if we do a line cut here, and we can see it's actually a pretty good zero resistance on both sides, and you have a very sharp phase boundary that separates the 2 phases. So if we take a more closer look to like a complete phase diagram here by density and the electric field, you can see actually it looks like it's being cut in half, and part of it is at Z1 we've seen in 0 magnetic field, and the other part of it is the new superconducting phases coming out. And of course, you can also check the Hall response, and in both sides, the Hall response is 0. So, I mean, with all these phases, if you put them together, it's actually give you a very rich phase diagram. So this is just the intrinsic piece of graphite. And you can get a whole lot of phase diagram that covers like a Wigner crystal superconductivity and all these correlated metals, and there's also even multiferroic phase. So it's actually a very nice playground, or even I would say it's an on-chip lab. So with this, you can test a lot of, hypotheses, and even searching for a lot of new stuff. And you can add in more flavors onto it. For example, by adding more potential, so you get even richer phase diagram. You have actually superconductivity that coexist with the fractional quantum anomalous Hall states. And you have all the CDW states, tree isolators, and all this kind of like very rich phase diagram. So overall, so this is a very nice playground, and you can even thinking about something more complicated. For example, the proposal of like joint fractional quantum anomalous Hall states with superconductivity that is maybe you may have a chance to see some more exotic quasi-particles like parafermions. And you can also thinking about like doing like more complicated device structure, for example, like a electron interferometer to check what is the statistics of the quantum particles. So yeah, with this, I would like to thank you for your attention, and yeah, please ask questions.
Hey, it sounds good. I was going to yeah, is that, and is it, is that the, what is the code card? Is it going to maybe just like they have it on the thing? Is it? I know how it's like.